A novel development of a biodegradable face mask. There's an insanely high demand for disposable face masks due to COVID-19, and this increase of disposable PPE use has resulted in improper disposal of this equipment, making it a new source of pollution. Because of this, there is a need for efficient, environmentally sustainable biodegradable face masks. Our main research question is, will a biodegradable disposable face mask using gelatin-based bioplastics be as effective in blocking particles as those on the market? Our hypothesis also states that if specific quantities of glycerol, gelatin, and water are mixed into a bioplastic, then a thin, biodegradable, flexible plastic sheet will be produced, and when associated with a filter into a face mask, it will have a 90% particle filtration rate compared to highly regarded N95 masks or surgical masks. Our objectives include making a bioplastic sheet and converting this sheet into a fabric-like material, which assembles into a face mask that will be tested with efficiently with little particle penetration and thickness, yet have high breathability and flexibility. Our materials include materials to make the to make the bioplastic, materials to assemble the face mask, and lastly, materials to test the efficiency of our mask. Notable materials include glycerol or glycerin, cornstarch, gelatin, water, and materials to assemble the bioplastic include a clothing iron, which would be used to iron the parchment paper and the resulting bioplastic. A canvas, coffee filters, 100% pure beeswax to make it water resistant, sewing machine, beads, metal wires. And testing materials would include food coloring, spray bottle, cardboard box, rubber bands, water bottle, ruler, hair dryer, and a candle. And lastly, we'd have materials to dispose, such as kitty litter.
Procedures and protocols. Assembly. The first step in our procedure is to combine glycerin, water, and gelatin or cornstarch to create the bioplastic. We will heat these materials over a stovetop, and after heating them, we will flatten and mold them onto a baking sheet. We will allow this to dry, and after drying, we will iron over parchment paper over the bioplastic to make it fabric-like. At this point in our procedure, we will have 3 layers: an outer and inner bioplastic layer surrounding a filtration material of either canvas, fabric, or coffee filter. Next, we will apply a waterproof wax of beeswax to give the outer and inner bioplastic layers waterproof qualities. Finally, we will assemble all of the parts, including the ear loops, together. These are some images of our procedure. After adding 12 grams of glycerol to the pot, we added about 5 grams of cornstarch and 30 grams of water. We heated these materials until it became a milky-like substance and thickened in the presence of heat into a jelly-like substance. Next, we flattened these materials onto a baking sheet and ironed it over. Procedures and protocols. Testing. Our first test is testing the bioplastic's particle filtration efficiency. We will spray the bottle from the inside of the mask at varying distances. The drops that will escape will be recorded onto a piece of paper parallel to the spray bottle and the mask. The number of particles escaped will be recorded. Our next test is to test the breathability of the face mask. We will blow a hairdryer through the mask at varying distances and determine the distance at which the adjacent lighter is blown out.
We will test the flexibility, fabric strength, and the thickness of the bioplastic. For testing the flexibility, we will first cut out a 5 to 6 inch hole in the base of a cardboard box. Then flip the box upside down and place the fabric over the hole with an empty water bottle on top. Finally, add 10 milliliters of water into the bottle until the fabric bends in, and then record the weight of the water bottle. For testing the fabric strength, first attach a rubber band on a hook and loop the mask around the other end of the rubber band. Then pull the mask until it breaks and record the length of the rubber band at the point at which this happens. To limit variability, rubber bands must be consistent in size and new each time. Lastly, for measuring the thickness, we'll simply use a ruler. We created various tables to show the breathability and thickness of surgical masks and bioplastics. On the top left, the data table shows the distance a candle can blow out for both masks. In the data table, it portrays that the average distance for surgical masks is 3.5 inches. However, the bioplastics distance is much smaller than the surgical mask, showing that it is less breathable. The pictures on the bottom left show the experimental setup for testing this. Meanwhile, on the bottom right, the thickness for surgical masks and the bioplastic is shown. The bioplastic is 0.6 inches more than the control, which can account for its lack of breathability. As you can see on the top right, this picture depicts the experimental setup for measuring the thickness of the bioplastic. As we have started the testing process, we have several limitations. Our main limitation is that our bioplastic is not as breathable as a surgical mask due to its thickness and hardness. However, we are using trial and error to figure out the quantities necessary for each component of the bioplastic. We were also unable to analyze whether cornstarch or gelatin works better in bioplastics, whether canvas or coffee filters work better as filters, and we were unable to test the particle filtration efficiency or the tear resistance of the face mask, but we'll make sure to implement this through trial and error in the future. However, despite these limitations, our mask has environmental and health applications. Firstly, since our mask is biodegradable, it benefits the environment, as it can drastically reduce the plastic footprint strengthened from face mask pollution. Additionally, it would have a profound impact on the health and well-being of the community, as we aim to have a 90% particle filtration efficiency, which is greater than both surgical and cloth masks. In the future, we hope to embark on projects relating to bioplastics, such as synthesizing biodegradable medical implants. We also hope to compare the efficiency of various masks either through a light scattering method or through analyzing the length of bacterial life on masks.